Welcome to the first Voxxed Days of Thessaloniki, and welcome to the web track. Okay. As my grandmother used to say, web track, best track. So the first speech, first presentation is from Ole Michaelis. It's actually one that I'm excited about. It's about HTTP2 and how it relates to HTTP1, what the differences are. Ole is from Germany, but he's a bad German, which makes him a good German, because he doesn't like beer or football. So he's one of us. If you like football, please get him. He's the founder of So Coded, which is a hackfest. He's also he's a backend engineer for Jimdo, which is help me out, Ole.
Jimdo?
Yeah, it's like
it's a website
for building your own websites. Yeah, well, website builder.
It's a big CMS.
A big CMS, and then he, in his spare time, he builds Slider.io, which is a website for easily sharing slides. And I will let him take it over from here. Ole Michaelis, please.
Yeah, thank you. Hey everyone, hi. So well, we're going like hard over time, I guess. But anyway, let's start. So welcome to the Whirlwind tour through the HTTP2 spec. First of all, I'd really like to know who of you is using HTTP2 in production already. So go your hands up in production. Wow, that's one hand. I do, and maybe you do too. If you're using Google Analytics on your website, you do too. So before I start, I really want to do a quick questions and answers, because whenever I'm giving this talk, people have a lot of previous knowledge in the mind, and they have a lot of questions already regarding this stuff, and I want to get this out of our way so you can follow the talk. So first question, is it really done? What do you think? Is it done? Raise your hands. The spec, done, 2 hands. It's done since 2 years. You should know this. Is SSL mandatory? Hands up if you think yes. No, it's not. But actually, all implementations you see in the wild, they only work on SSL. So in the spec, it's either, but in the actual browsers and servers, it's mostly only SSL. Is it made by Google? Hands up if you think yes. One hand. Yeah, well, no, it's not. Well, what's speedy? It's just a different protocol. It's just something completely different. But obviously, in the consortium where they did the spec, there were a few Google engineers, but there were also a lot of others, and it's not company driven. Is it plain text? Hands up if you think yes. One hand. 2, 3. No, it's not. It's binary. Headers compressed. Hands up if you think yes. Oh, great. That's almost everyone. Yes, headers are compressed. Oh, that's my favorite one. Will HTTP1 still work? Hands up if you think yes. Obviously. Browsers still support HTTP1 and will break the complete web if we would stop supporting it. So don't do this. In order to understand why HTTP2 is awesome and to understand the problem it fixes, you first have to understand the problems of the protocol we have at the moment, which is HTTP 1.1 mostly. So, in 1989, Sir Tim Berners-Lee imagined his vision of the World Wide Web, sharing documents between the MIT and the other institutes like CERN. His vision was that browsers even could function as editors to the documents, right? This did not happen, but this is what he was thinking of. And then just 2 years later, the first version of the HTTP protocol got into the consortium. Then in 1992, there was the first 1.0 draft, and it took them a few years to actually finish the draft and write the protocol. So in 1996, HTTP 1.0 was released in RFC 1945. I have a lot of RFC numbers in this talk. I actually love reading RFCs. It's a bit weird to read them. It's sometimes hard to understand it, but it's like the best piece of paper I've ever seen with when it comes to condensed information. So all the information in the single sheet of paper is like the highest if you ever start reading RFCs. So that's really something I can recommend. Well, as you can see in the next bullet on the slides already, it only took them 1 year to figure out what they just built was bullshit, right? So they replaced version 1.0 with 1.1 just 1 year later. It was not that bad, so one still works, but it has hard performance drawbacks. Well, in 1989, RFC 2326 was released. Does anyone know what that is? Hands up if you know that. Okay, great. So I can share my trivia with you. Well, it was released on April 1st. And actually, it's a spec describing how connected devices should behave when they are making coffee. So it's like interconnected coffee machines. And this specifies the HTTP status code 418 IMT protocol. So if you ever wonder where this comes from, that's RFC. So let's move on. In 1999, they replaced the previous version of the HTTP 1.1 spec. So the protocol itself didn't change, the spec changed a lot. It got shorter, it got more condensed, the body was more concise, all this kind of stuff happened. And then 2007, well, in between there were a lot of additions to the protocol in different RFCs. But the protocol itself didn't change. I don't know, cookies, for example, right? This stuff came up, and then in a different RFC, caching, all different layers of caching, all there was in this time frame, but in different RFCs. So in 2007, the IEFT, which is the Internet Engineering Task Force, which is responsible for doing all the HTTP protocols and RFCs, they formed the HTTP BIS working group. And BIS, as far as Google Translate told me, is Latin and stands for two. So in 2012, the IFT started the call for proposals. And this is where Speedy comes in, because Google actually proposed that the Speedy protocol they were working on internally as a base document to work on HTTP2. So this is why a lot of mechanics from the Speedy protocol are still present in HTTP2. And this is the relation they have, right? So Speedy is kind of the base version. And you will, at later points in this presentation, still see some pointers to the Speedy protocol. So let's move on. So in 2014, there was the HTTP 1.1 split. So there were over over a dozen HTTP related RFCs. And it was really hard as an implementer to implement the full spec because the information was spread out everywhere. So what they did, they completely made the old one obsolete. And while keeping the actual protocol, they rewrote all the specs. So they split it up by themes and came up with a new set of HTTP 1.1 related RFCs. In May 2015, the protocol was actually released, so there was one missing signature from the IFT on it, and it was released as RFC 7540. Well, at the end of last year, which is now almost a year ago, I'd say, 22% of all web traffic is HTTP or was HTTP2 already. There was just last week where they announced new statistics from Firefox that over 50% of the whole web traffic was SSL already. And as I mentioned, SSL is kind of the prerequisite we have to run HTTP2. So we are really on the way to do this. And on all encrypted connections, 35% already were back last year on the new version of the protocol. Well, when we want to talk about HTTP, I think we should talk about the basics first. And with that, I'm talking about HTTP 1.1 here. First of all, it is plain text, right? So if I just spin up my console here, I can just open up a TCP connection to google.com on port 80, and this is all plain text, right? So the connection is now established. You can just type the actual request. So I have the status line, so it's get / and then the protocol version number and the host. So the host is mandatory. And then just do 2 times like new line, 2 times enter. And then the server will respond. So this is a valid request getting a valid response just by typing on my keyboard, right? This is an amazing feature of the protocol, and it allowed us to do all this great introspection. You know, you can just read the wire, but on the other hand, it also had a big security drawback, right? You just have to be somewhere in the middle, and you can read all kind of stuff like passwords and all this. So it's plain text, and this will change. And also, it is stateless, right? Every request should contain all the information for the server, for the receiver, to make sense of the request, right? So it's not that there's state on the one side or the other. I mean, there might be state, but to reference it like a cookie, right, or a session, you always have the identifier in the request passing it back and forth. So there's no state on the between the requests. And it's super flexible, right? Imagine when I was just sharing Sir Tim Berners-Lee's version or vision of the web. So documents, interconnected documents for research institute. And nowadays, what do we do, right? I mean, I'm earning my income, I'm earning my money, all the money I get from the web, right? I work at a company, we're building websites. I just built this letter thing just on my own. We build applications in the thing, right? And if you would told Sir Tim Berners-Lee about Tinder, I think he would not believe that. But I mean, this is what we did, and it's all based on these foundations, right? And it has changed a lot since the invention, but with this, there are a lot of problems, right? It was not meant to support the use cases we have. You do media streaming, right? Media streaming on a protocol which was meant to share documents. This obviously doesn't work pretty well. So first of all, this is what I just said, the web matured a lot, right? So the total number of requests and the total request size almost doubled in the recent years. And then you have 38 connections on a single page load, right? You just have one page loading, and you have 38 different TCP connections. And thus you must know that every TCP connection, especially if they're encrypted, has a lot of requests and TCP packages going back and forth. And in nowadays networks, we have a great bandwidth, right? With 4G or DSL or fiber, like our throughput is amazing, and receiving big documents is not a problem. But especially if we're talking about latencies, this is the biggest issue we have, right? So getting a request, a single package from our side of the Atlantic Ocean to the US takes 150 milliseconds. So if you want to establish a connection from here to a socket in the US, and it's encrypted, you have to go 6 times back and forth. So 6 times 150 milliseconds per TCP connection. This is crazy, I think, right? And I'll have an example in a second. And then it also suffers from a thing it's called request on answer, which actually means once you receive the document and parse it can actually trigger more documents to be received. Think of you're receiving the index HTML here, and then you parse it, and then you found the CSS, and then the CSS might have some other resources to be loaded, and then there's all this weird JavaScript kicking in, right? So JavaScript loads more and kicks some complete no rendering pipeline, and it all adds up to this really, really crazy latency thing. So let's check an actual example. And I've not made this up, right? This is The Verge. This is some news site I don't use, but it's a great example of how the web works. I don't want to blame them too hard because there's tons of different sites acting in the same weird step. So if I just load the website, so I have a video here for you from a network tab where I just loaded. So this is real time. So I'm loading, and you see the first request. Somewhere here, it's gone already. So you see this waterfall pattern, right? It goes down, and it's still loading. Okay, I think it's done now. It has a lot of requests on this, right? So here we have this. So the video I just showed you was a bit older. It was almost a year when I first created the slide deck. And this screenshot now is just a month old. And I just did the same experiment again, but I didn't record a video. So if we zoom in, like, what the fuck? 250 requests? This is 10% of my data plan I have in this country. Just for a single page load, right? And it takes 20 seconds, like seriously, 20 seconds until it's loaded. Oh shit, what? This cannot be the state of the web, right? I don't want to accept this. I think we should change this because we are the developers, we are creating this, and it's our responsibility to make this better. And I really want to encourage you to just load your site without a warm cache, right? And then check the stats. So there's also a problem called head-of-line blocking. This actually means, well, you can share TCP connections, right? So you can have a single TCP connection transferring different documents on it. And this is what happens. So the browser sends 3 requests in a row, and then the server can respond. But this example here is actually a pretty good to demonstrate the problem, because while the index HTML could be something dynamically created, right? It could be your Java thing or PHP, Ruby, whatsoever, creating the HTML document, and the assets, like the CSS and the JavaScript of the images, it's static. So in theory, creating this takes really long, and serving the other ones can be pretty fast. But the protocol has no function of identifying requests. So the only option the server has is to wait until the first document is resolved, because it has to maintain order, right? This is called head-of-line blocking, and this is one of the worst things which ever happened to the web. But this will be fixed in HTTP2, so we'll come back to this later. So head-of-line blocking, the automatis, right? The slowest request always blocks. There are basically no workarounds because it's an issue of the protocol, and therefore it's often unused. So if you check your browser connection sharing, it's often just disabled just because of that. As developers, we really enabled it. We tried everything to work around this, right? We had the worst ideas of fixing this. So we came up with the idea of having sprites, right? Putting all our images together. In a perfect world, there would be no need to do this, right? Because we're fucking with our cache, right? If we just replace one image, we have to transfer the whole sprite again. So that's shit. We did all the weirdest things of concatenating, right? So putting all the assets like next to each other, so to don't have all the latency round trips. We sharded all our assets between domains because browsers are limited to 5 concurrent TCP connections. So you have assets 1, assets 2, assets 3, and this kind of weird domain names. We do all this like pre-configuring and inlining of images, for example. Well, when they're small enough, we can just inline it and then make the initial document big enough. This fucks with all the semantics we have in the web, right? Your HTML is not semantic anymore if there's a base encoded image in it. And then this is the worst. We have all the weird like preloading hacks. So if you come to my landing page, I'll just give you my application JavaScript so your browser doesn't have to request it. Well, this violates all kind of software design rules I know. Right? And then we do cookie-free domains. You see this as asterisk because I think this is a good idea, and I really want you to keep this. In general, we try to save requests because multiple requests gave us the latency penalty. And HTTP2 is here to fix the latency penalty. So let's talk about how HTTP does that and how the protocol actually looks like. First of all, the protocol is compatible. It's not going to break the web. The scheme will stay. HTTP will stay HTTP, HTTPS will stay HTTPS. The user will never see this. All kind of mythology, like headers, request response cycle, and the HTTP methods, all of this will stay. This is not going to change, and your application can basically just look the same. Well, you might wonder how upgrade looks like. First, the upgrade part you probably don't need, and I just saw I threw it on the slides. Well, so the upgrade part is basically, it's a header. So there's an upgrade header, and there's no status code for it. And this makes the upgrade work. Well, this is the one you really need, because this is one happening in your browser probably already every time you load any web page. Because as I mentioned, the big players already switched. So Google switched, Twitter switched, Facebook switched. They already switched to HTTP2. So whenever you're surfing and browsing, you probably send a lot of HTTP2 already. Well, you must know about ALPN, which is specified in RFC 7301. ALPN stands for Application Layer Protocol Negotiation, and actually this is not the full abbreviation. The full abbreviation would be TLS ALPN, which is Transport Layer Security Application Layer Protocol Negotiation. Actually, this inherits from NPM, which is Next Protocol Negotiation, which was the protocol negotiation part for SPDY. So here you have the first SPDY reference, right? So this is basically just another name for NPM, and as the name suggests, it's an addition to the TLS protocol. This is an SSL handshake, lots of awesome stuff going on here, but this one is the important line. So the client actually offers a list of protocol it supports, and the server just picks one. That's it. So a little heads up, so we have H2 and H2C, and as we have with HTTP and HTTPS, there's like a short and a long one. But here, the short one is the encrypted one, and this one is clear text, right? And this is also a hint that the implementers and the spec writers want you to know that this is the default. Encrypted is the default, this is the exception, right? So connectors are multiplexed, and this is how they fix the latency issue. And a multiplex stream or multiplex connection basically means that you can transfer multiple resources on a single connection at the same time. So physics is not concurrent, right? A physical connection can be concurrent, but the way to make this work is actually have the multiplex connection. It looks like this. So first you have this physical TCP connection, and these connections holds logical streams, and each logical stream then has multiple frames. So a stream is usually one request-response cycle, and every stream has multiple frames, and the frames are binary. So let's take a look at the frame layout, because whenever we're talking about binary protocols, this is what you see quite often, right? So this is the HTTP2 header here. It has a length, it has a type, it has some flags, it has a reserved bit, which is always 0, then there's a stream identifier and the payload. This header, this frame header is above every other frame you will see, right? And in the next examples, I will just don't have this. Well, when I was reading the spec, I stumbled upon that one. It's always 0. Like, well, why do we put it there? Just leave it? I mean, we could save so much traffic. But what I just learned when I asked why it's there, it's to support platforms which does not have support for unsigned integers. Okay, imagine how much traffic we create just for this. Well, let's talk about the different types of frames we have. The first one, and this is the one you might see the most of the time because they're probably one of the important ones, is data, right? So this is just binary or maybe even clear text data whatsoever, transferred on the wire, so you can transfer assets, you can transfer documents, you can transfer whatever you would transfer in a response body or a request body. This is a priority header, and it uses a priority tree. We'll talk about this later as well, if time permits. Then there's reset stream. I think this is pretty important because if there's a failure on the wire or on a single stream, it does not and should not lead to the whole connection to blow up, right? So it's just one connection resetting and the others should continue working. I mean, it depends a lot on the platform you're running on, but the cool platforms like Erlang, they support this kind of features. And then there's a settings frame. Well, it's a settings frame. There are a bunch more. There are like 9 different ones. I think this one's pretty interesting. I just filled it with real binary data, so this is an actual request on the binary stuff, what it would look like. You see a ping request with an acknowledgement flag. So here you see the length, and the length is in this case specified by the protocol. And then here you have the type, so the type is 6. And then the flag, so the flag is 1. All the type and the flags are specified in the actual protocol. And then we have the troll bit and the stream ID. What I really like about the stream ID is when I take a look at it, I can tell you that this is a server sent one because clients have odd numbers and servers have even numbers. Well, and this is just some opaque data which is required by the spec because it should not have nobody to be to be a real frame, right? So with all of what I showed you now, you could be able, or you are able to implement the same features your server already has, right? And you would fix the latency issue. I think this is great as it is already. But HTTP has also a bunch of more stuff it could offer to enhance the user experience. Right? And the first one, and I think one of the most important features of HTTP2 is a thing called server push. Think of server push as a direct connect. What is going on? We have 3 cameras here and they're all taking pictures. No, you're taking pictures of each other. What are you doing there? Okay, anyway, sorry for the interruption. Okay, server push. Server push, think of server push as a direct connection between the server and the browser's cache. So for your application, for your JavaScript and stuff, there's no way to interact with it, but the server can actually tell the client that the client is going to need a certain asset. So think of you're requesting some index HTML, and while the server is rendering it, like it's PHP and it takes very long, the server can just tell the client that it is going to need the CSS file and already start sending it before the browser has ever seen the actual document. I think this is amazing. And this will enable a big performance improvement on the web in the following years. So that's how it works. This is the push promise. This actually just looks like the header frame because it is actually, it's basically an HTTP2 header, but it lacks the request. This is why it's different. And that also offers flow control. Flow control actually means if you have multiple frames on the wire or in the queue to be sent, you can reorder them depending on how the priority is of a certain package. So think of the document and server push frames. So the document should have a high priority, right? Or maybe think of images and JavaScript. So you probably want to give JavaScript some more priority because it's for your application more important to run rather than images to be there, right? But again, this completely depends on the app. Maybe images are more important. But then tracking pixels, for example, tracking pixels have a really low priority because the application and the user experience is way more important than tracking. At least it should be. Well, and it uses a thing called weighted dependencies, and it works like this. So it always, first off, builds a priority tree. So let's build up one together. This is completely made up, but I think it illustrates the function pretty well. So what do we have here? Well, we have the stream ID 0, and the connection always starts with stream ID 0. And then we have stream ID 3 and 5, and this one is the weight. And as you can see here, stream ID 7, 16 is the default weight. And all the, imagine of like 100% of the available traffic coming into stream ID 0. And then stream ID 7 should receive 2/3 of the available resources, and stream ID 7 should receive half of the resources available of stream ID 3. Sorry. So this makes any sense. This is how it works. And with that, you can use really fine-grained priority trees. This is the example of the Firefox dependency tree. I think it's important to note that the Firefox dependency tree is actually the most efficient one. I can't tell you why it is that way. I know that the IE, for example, it doesn't make use of it, so it's like completely flat. Every request just depends on 0. And Google, their dependency tree, at least like half a year ago when I created this, was still optimized for the speedy protocol. This is why it was not like, and Firefox just like they created it for this. So it worked better. So well, how does Firefox do it? And I think that's pretty interesting to see it in the wild. So first thing, stream ID 0 is initializing the priority tree. And then it does some more initialization. So this is the tree it builds, and there's no data like transferred yet. It's just setting up the tree, setting priority headers, right? And then we have the first actual request. So that's the HTML, and that goes there. Then it might also find some CSS in the HTML, and it goes here. And then we have some JS in the head section. It goes there. Then the images go next to the HTML, and then there might be some JavaScript in the footer, and it goes there. I think that's pretty interesting that they do it this way and that they make use of this feature. I can't repeat why they're doing it that way. You can find the link to the talk where it basically copied this from. It was in a conference in Japan, and the implementer of them gave a talk about this. And if you really want to know like how this works, I really can encourage you to check this out. Then there's a thing called compressed headers. We talked about this at the beginning. So headers are compressed, and it works pretty efficient. So this is how the header frame looks like. It has the padding, the stream ID dependency, the weight, and the header block fragment. So this is binary data. And the header compression is specified in different RFC. The mechanic it uses is called HPAC, and it is written down in RFC 7541. And I really want to give you an intro on how this works, because I think it is amazing and it's really efficient, and you can tune your application a bit to make this work better. So this is the request header we want to compress. HPAC uses a mechanism called header compression table. It consists of a static part and a dynamic part, but as you can see, the indexing continues. So if you want to compress the header method get, you can just reference it by the ID 2. And if you have another header where the key, the value is not in the table, you can reference it in different ways. So this is how the compressed version looks like, right? So I have method get header, and it's in the static table, so I can just reference it by that. And method get is something you see on the web all the time, right? And then there's also a mechanism to put stuff in the dynamic table. So the connection can decide, and the sender can decide what is going to be in here. So with user agent, for example, right? It won't change on subsequent requests. So it makes a lot of sense to put it in the dynamic table and then just reference it in the subsequent requests just by an ID. Two things to note here. First, 51, that's wrong. There's a typo, but it's not on my slide. The slide is correct. The spec has the typo, and it's by intent. I don't know if you know this, but when they wrote the first HTTP spec, referrer was spelled wrong, and they kept it that way since forever, ever since. Right? They didn't change it back, and if you take a look at the implementations, usually both versions work. I think that's pretty interesting to note. And also, and I do see a big deal breaker in here. You see this dynamic table, and it has state. So this kind of breaks the rules of HTTP. So in subsequent request response cycles, this one carries state over requests. I don't see this as too bad, because it's just on a single TCP connection. So if you have two connections, they both again build up their own dynamic tables. But this really changes the protocol a bit. It doesn't change the actual HTTP2 implementation because it's in a different spec. But there is state. And the strings are encoded in a way called Huffman encoded. And I really want to do a really quick demo. I try to do it in below a minute, so I have to be really fast. So if you want to try to encode the string Mississippi River, what is going on with this sound? Right, so if you want to, I can't hold the minute. Okay, anyway, so if you want to compress the string Mississippi River, we have 70 characters, each character is 8 bits, so we have 136 bits, sorry. First thing we do is we count the characters by occurrence, so we have 1M and 5Is and so on, and then we order them by occurrence. Then we just concatenate the characters and sum up the values, how often they occur, and by that we can build up the tree. Okay, and we always do the lowest numbers. And then we walk down every branch of this tree while we are assigning a 0 to the left-hand side and a 1 to the right-hand side. By this, we can build up a binary tree and get our encoding table. That's an encoding table. So if you want to encode a 1 and an I, we just send 2 zeros. This is how a Huffman encoding works. This is the compression table, and with Huffman encoding on this string, we would save up to 70% of the space used. Even though it's not as efficient as the index encoding. Right? So the index encoding works way better. Well, all this is pretty nice and sweet and shiny, and your question might be, well, can I use it now? And is it here already? Well, let's take a look on how HTTP looks in the real world. First of all, it is already here, right? It's not something super scientific, only existing in papers. Even though I'm referring a lot of papers, every major browser in the recent version has support. This is support here. if we would have Wi-Fi, I would just do some demos, but you can just copy this from from my slides. And this is the ng HTTP is a tool to debug HTTP2, because it's not plain text anymore. You would need, like, the tooling has to improve. The tooling is already here, so don't worry about that. But this gives you a really nice introspection into how an HTTP connection works. And the first thing you would see if you do this is that even the ng tool in the default configuration opens up 9 streams, right, just to receive a single document, because it doesn't, like, when it makes a request, it doesn't know if there are more requests to follow on that. And then these are just 2 demo sites. Yeah, they look pretty well. Let's take a look at the implementations. First of all, let's take a look at the browser side of things. Well, as I mentioned, every major version of the browser support. You might know, can I use? There's the website to know the browser version has support, and you should use it or not. And yeah, well, in this display, you can see that it actually works pretty well on all recent versions, and these are the come, that is, and it also supports the view, which I think is way more interesting than relative features. Right, and what we see here is that there's a lot of stuff going on, and it's mostly green, right? And then here, that's the Android browser, and Opera Mini. And this one is, I don't know which browser. I don't even know what it is. Well, if you take a look at this, and then think of your application stack, this one really shines out, right? And I wanna ask you, why the fuck are you optimizing for this? Right? What about these people? They could receive, like, double your page, like half of your page load time you have. So you could double the performance by switching. But you're still optimizing for Opera Mini and Android stock. And this is not even Chrome on Android, right? This is stock. Let me fix the mic really quick. Yeah, all right. Okay. And then let's also take a look at the sub-implementations, right? Because browsers have this, but I don't. Well, I don't know what web server you're using, but yeah, let's take a look at the market share, because the market share is also, like, in order to understand, like, the impact of something, I think the market share, especially in this distributed web stuff, is important. So first, Apache is almost 40%, then IIS is almost 30%, Nginx has 15%, then there's the Google Web Server with 2%, which I think is pretty interesting because you're not able to deploy this on your own, right? So of the all web traffic, the Google Web Servers have 2% market share. And then there are all the others, like Netty, Jetty, Puma, you name it. Basically the web server, like, mostly it's language dependent implementations and stuff. So for Google Web Service, we don't know. But we know that they dropped support for Speedy February last year, so probably they had support since then. Apache did it, like, since 2.4 or 2.4.12, which is out since July. Nginx has support since September last year, and even IIS, so our poster child Microsoft, they have support since Windows 10 and Windows Server 2016. So I want to repeat my question: why are you not using it at the moment? Well, your argument might be, oh, that's so complex to configure, and no, it's not. So let's take a look at the Apache conf. I don't like Apache conf, by the way, but well, it's a one-liner. This is like that's oh, sorry, that's too quick. So let's take a look at Apache again. This is a one-liner, right? That is everything you need. This is optional. You need one line to enable HTTP2. That's it. You don't have to configure anything. The defaults work pretty well. Just do this one line. Then Nginx. Nginx is my favorite example. That's Nginx conf. That's the line, and you have this line already, right? This is opening the SSL connection, so it's what's it? 5 characters. If you have a recent Nginx version, just put these 5 characters in, and you would double your performance. Why aren't you doing it? So let's talk about third-party stuff. Fastly just recently announced the limited availability. Amazon announced the application load balancer, so Amazon Web Server has support. Cloudflare already has support, and the major players already they're coming up now. So even third party, they're getting there, right? And as I mentioned at the beginning, I don't want to leave you out with the old stuff, right? Because it's 2 years old already. I want to give you an outlook on what is coming in the future. And the first thing is cache digesting. So cache digesting means that with server push, we have this nice feature, but it kind of is built up on the assumption that the client always has an empty cache, which is for most websites not true, right? You have something in cache. Maybe it's because the web developers use this CDNify CDNs, or I don't know. It's just a recurring customer. And sending a recurring customer the same assets all over again wastes a lot of bandwidth, it wastes a lot of server resources, and it just doesn't make sense at all. And cache digesting is a way that browsers can tell the server what they have to cache and how fresh it is. And then there's quick. Quick is sometimes in the web referred as HTTP2, which is complete bullshit. I never do this. Don't show anyone in the community this slide because they will pay me for that. So quick is basically, it replaces the TCP part in HTTP2. So quick is HTTP over UDP. Think about this. Well, it might sound really stupid in the first place, right? Because if you're missing a package, like a single package on your actual document, this would be pretty bad, right? But Quick has an awesome, mechanics to work around this. And if you know hardware rates, RAID 5, for example, they have this data parity, so every disk contains enough data to restore a failing disk. And this is basically what Quick does. So every package contains enough parity data to reconstruct missing packages. This is a pretty crazy approach. Google is already using it, so if you're surfing Google websites with your Chrome browser, you're actually using Quick already. And yeah, it works. I think that's pretty crazy. And then lots of other stuff coming out, but I really want to talk about that point because I think as web developers, and I don't know if you identify as such, we are just holding it wrong. We're just doing so many things wrong, right? We are not using all these features. And then I've seen so many people, they enabled HTTP2. For example, 99 Designs, they enabled it, but they didn't change the infrastructure. So they still had all this concatenation. They still had the domain sharding, which is really the worst. All these features I just mentioned, and the multiplexing and all of this, really only gets the benefit if it's on a single TCP connection. You have to have the single TCP connection. And if you switch, you should adjust your complete architecture as well, right? Don't just enable it, even though I just kind of recommended it, and it will give you a little bit of a boost depending on how your app is set up. But you should really switch, like get rid of spriting and get rid of concatenating, get rid of your bundles and stuff. So I want you, in the first place, stop concatenating, stop spriting, stop domain sharding, and even though this might be a really bold statement, I know at least one person in the room really hates me for this, trash your asset pipeline. You don't need it anymore. And have you ever used Babel? Who of you has used Babel before? That's a few hands. Do you like it? It's like, whenever I touch it, I like, I don't know, that's the most complex thing a software developer can ever use. It's like writing binary data by hand. I don't know, it's so complex, it doesn't make any sense, and it solves the problem, it just solved the problem on the wrong layer, right? We are solving all the problems the web and HTTP1.1 had on the wrong layer. It should have been done with a mechanism like HTTP2 just 10 years before, and we would not have all this trash. Well, I probably know you won't do this, and I think that's okay. I just want to, in order to make a point, you have to go to the extreme. And I think the extreme would be to trash the asset pipeline, or at least simplify it. Right? And then that's also something I already mentioned. Don't just upgrade. Don't just upgrade to HTTP2. Just use it. So get everything back to a single to a single TCP connection. This is really the most important part. Well, this is an obligatory introduction. My name is Ole Michaelis. If you have any feedback or any questions, because I know we're running short on time and I don't want to be, I don't want to be overtime or too much overtime, even though I'm running really late already. Just follow me on Twitter. This is like the best way to get in contact with me. Really love this thing. If you're into following on GitHub, you can do this as well. I don't know, I don't understand this. I have a blog where I don't blog. I don't know if you want to use that. There's some old stuff on there and some nice pictures. I want to get these on the site as well, some awesome side project stuff. That's it. That's all I got. Thank you very much for your attention.
Thank you very much, Ole. Very useful stuff there. Unfortunately, we don't have time for questions, or we do, but it's going to eat into your coffee break. So you can all go out for coffee. We have 20 minutes, but in 20 minutes the next talk is going to start. So please be here by 20 to 12.
I'll be here all day. Just find me if you have questions. Right?
That works as well.
Break.
Thank you very much.